Welcome to Sleepless Scientist, the channel that brings you science made for relaxation and sleep. Tonight, we're taking a journey through the restless heart of our planet, one that rumbles beneath our feet, shakes our cities, and sometimes refuses to let us ignore its power. We're going to talk about earthquakes, why they happen, how they work, and what they reveal about the secret life of the Earth. Thank you for tuning in. If this video happens to keep you awake instead of putting you to sleep, I truly apologize. But if you enjoy this kind of content, please consider giving it a like, subscribing to the channel, and leaving a comment about where in the world you're watching from and what time it is for you right now. Let's begin our journey deep into the planet. The story of earthquakes begins in silence, far beneath the crust of the Earth, where vast forces play out in slow motion. Unlike dramatic explosions or sudden volcanic eruptions, the machinery that causes earthquakes grinds away quietly over millennia. The Earth's outer shell, known as the lithosphere, is made up of rigid plates that float on the semi-fluid asthenosphere beneath. These tectonic plates are constantly moving, although the motion is agonizingly slow by human standards. On average, they shift at about the rate your fingernails grow, roughly 2 to 5 centimeters per year. It doesn't sound like much, but the consequences of these movements are anything but quiet. There are 7 major tectonic plates and numerous minor ones, and their borders are where most earthquakes happen. These edges are not neat or tidy. They are jagged and rough, with massive friction resisting the motion. When the plates move, stress builds up along these boundaries. The rock on either side of a fault line becomes deformed, storing elastic energy like a giant spring being compressed. Eventually, the stress becomes too much. The rock breaks, the energy is released, and the ground begins to shake. This sudden release of energy is what we call an earthquake. The energy released in an earthquake travels in waves. These seismic waves radiate outward from the point where the rupture began, known as the focus or hypocenter. Directly above it on the Earth's surface is the epicenter. The most common type of seismic wave is the P wave, or primary wave. This wave is compressional, like sound, and travels the fastest, moving through both solid rock and liquid layers. It is followed by the S wave, or secondary wave, which moves more slowly and can only pass through solids. Finally, surface waves travel along the Earth's exterior and are usually responsible for most of the destruction. These waves can roll the ground like ocean swells or shake it sideways with brutal intensity. Not all earthquakes are created equal. Their magnitude is measured on a scale that estimates the energy released during the rupture. A magnitude to quake might go unnoticed. A magnitude 5 can rattle dishes and nerves. A magnitude 7 begins to cause structural damage. And beyond that, things escalate quickly. The largest earthquake ever recorded occurred on May 22, 1960, in Valdivia, Chile. It measured a staggering 9.5 in magnitude. The quake lasted approximately 10 minutes and generated tsunamis that reached Hawaii, Japan, the Philippines, New Zealand, and even the west coast of the United States. But it's not just the magnitude that matters, depth and location also determine how destructive an earthquake can be. Shallow earthquakes tend to cause more damage because their energy has less distance to travel before reaching the surface. Most of the Earth's most powerful earthquakes occur along subduction zones, regions where one tectonic plate is being forced beneath another. These zones are inherently unstable, creating pressure cookers of stress over decades or even centuries. When that energy is finally released, the result can be catastrophic. Earthquakes are not rare. In fact, according to the United States Geological Survey, there are over 500,000 earthquakes detected globally each year. About 100,000 of these can be felt, and around 100 cause significant damage. Some regions are far more active than others. Japan, Indonesia, Turkey, Mexico, and California are among the most seismically active regions on the planet, thanks to their proximity to active plate boundaries. The infamous Pacific Ring of Fire, a horseshoe-shaped zone stretching around the edges of the Pacific Ocean, is home to roughly 90% of the world's earthquakes. And yet, earthquakes can also strike in unexpected places. In 1811 and 1812, a series of massive earthquakes rocked the New Madrid region in the central United States, an area far from any active plate boundary. These intraplate earthquakes are a reminder that seismic activity can happen nearly anywhere, although it is much more likely along fault zones. The science of studying earthquakes is known as seismology. Scientists use instruments called seismometers to detect and record ground motion. These devices are sensitive enough to pick up the tiniest tremors, allowing researchers to analyze patterns, estimate energy release, and determine the structure of the Earth's interior. Seismologists have created detailed maps of earthquake-prone regions, established early warning systems, and even contributed to the design of safer buildings and infrastructure. However, despite all the data, predicting exactly when and where an earthquake will strike remains one of science's great unsolved challenges. Earthquakes do not follow predictable schedules. They can strike without warning at any time of day or night. Sometimes small tremors signal an impending larger quake. Sometimes they don't. Some earthquakes come in swarms, a series of small and moderate quakes clustered in time and space. Others come with foreshocks, smaller quakes that precede the main event. But there's no consistent pattern that can be universally applied to forecast earthquakes with confidence. Still, there have been advances. In some countries like Japan, early warning systems can detect the first P waves of an earthquake and issue alerts seconds before the more damaging waves arrive. These few seconds can give people time to duck for cover, stop trains, close gas lines, or halt delicate operations in hospitals and factories. It's not perfect, but in a world where seconds can mean lives, it's a step forward. When the ground stops shaking, the real work begins. Earthquakes leave behind shattered buildings, ruptured roads, broken pipelines, and devastated communities. The human costs can be immense. The 2010 earthquake in Haiti, with a magnitude of 7.0, killed over 220,000 people. The 2004 Indian Ocean earthquake and tsunami caused more than 230,000 deaths across 14 countries. And the 2008 Sichuan earthquake in China left 87,000 dead or missing. And yet, despite this, life returns, cities rebuild, families heal. Earthquakes, as violent as they are, also reveal something powerful about the resilience of human societies. They remind us of the dynamic nature of our planet. They are not just natural disasters, but natural processes, deeply rooted in the way the Earth works. And while they shake our confidence and rearrange our lives, they also offer opportunities for scientific insight and deeper understanding. Deep within the Earth, the movement that causes earthquakes is not chaotic, but governed by an ancient and relentless system. The engine of this movement is plate tectonics, a geologic ballet that has shaped continents, raised mountain ranges, carved ocean basins, and yes, fractured cities. It operates at a pace so slow that from the surface it might seem that the Earth is asleep, but the crust is never truly still. It is always shifting, subtly bending and warping in response to pressure that has been building up for years, decades, or even centuries. There are three main types of tectonic plate boundaries, and each plays its own seismic tune. At divergent boundaries, plates move away from each other, often under the ocean. Here, magma rises from below the crust, forming new oceanic lithosphere. And pushing the plates apart, earthquakes at these boundaries are usually shallow and less intense, though they occur frequently. Then there are convergent boundaries where plates move toward one another. These are among the most dangerous zones, as the collision of continental or oceanic plates creates immense stress. One plate may be forced beneath the other in a process called subduction. And when that stress is released, it can trigger colossal earthquakes and tsunamis. Finally, at transform boundaries, plates slide past each other horizontally. This lateral movement produces earthquakes like those seen along California's San Andreas Fault. Within these zones, faults are the specific fractures along which the movement happens. Some are miles deep and stretch for hundreds of kilometers. Others are smaller, but still capable of producing powerful shocks. A fault doesn't need to be massive to be menacing. In fact, some of the most devastating earthquakes have originated from short segments of buried faults previously unknown to science. The more we study faults, the more we understand that the Earth stores energy in unpredictable ways. One might wonder why the Earth doesn't simply relieve pressure gradually, rather than saving it up for a massive release. The answer lies in friction. Rocks along fault lines don't slide past each other easily. Their rough edges stick, and the strain builds up. This is known as the elastic rebound theory, when the stress overcomes the friction holding the rocks. Together, they snap into new positions, releasing energy in the form of seismic waves. After the initial rupture, the rock continues to adjust. That's why aftershocks often follow a major quake. These smaller tremors are not afterthoughts, but part of the readjustment process as the crust settles into a new equilibrium. Aftershocks can last for days, weeks, or even months. In some cases, they are nearly as destructive as the main quake. Their unpredictability poses significant challenges for rescue and recovery efforts, especially when structures weakened by the initial tremor are brought down by subsequent shocks. Understanding the pattern of aftershocks has become a field in itself, with scientists modeling sequences based on previous events to help emergency services prepare. The Earth's crust, while solid to us, is really more like a patchwork of jigsaw pieces drifting atop a deeper, more ductile layer. The asthenosphere beneath is not liquid, but behaves like a slow-moving plastic. The heat from the Earth's interior causes convection currents in this layer, driving the movement of the plates above. The boundaries between these plates are often jagged, irregular, and locked together, creating zones of immense tension. Think of it like rusted gears grinding against one another. They move eventually, but only after great resistance. Human history has always been shaped by earthquakes. From ancient temples reduced to rubble to modern megacities brought to their knees, these tremors have left their mark on every continent. The destruction may seem senseless, but it has often spurred innovation. Ancient Japanese pagodas, for instance, were engineered to sway with the ground rather than break. In Peru, Incan walls were built with interlocking stones so precise that no mortar was needed. And these walls still stand today, even after modern buildings have crumbled. Modern engineering continues to evolve in response to seismic threats. In earthquake-prone regions, buildings are designed to flex, not resist. Base isolation systems use rubber and steel bearings to decouple structures from ground motion. Dampers absorb energy much like shock absorbers in a car. Some skyscrapers are topped with giant pendulums, tuned mass dampers that swing to counteract swaying caused by earthquakes. These feats of engineering turn the unpredictable chaos of the Earth into something survivable. But, for all our ingenuity, nature still has the upper hand. Some earthquakes occur with no warning in areas with no known faults. Others rupture previously unknown fractures, throwing even the best scientists into a scramble to understand what happened. Despite advanced monitoring networks, precise prediction remains out of reach. That doesn't mean we're powerless. Earthquake drills, reinforced infrastructure, and emergency planning save lives. The goal isn't to eliminate risk. That's impossible, but to reduce vulnerability. Culturally, earthquakes have inspired awe and fear for centuries. Ancient myths told of gods striking the ground in anger, or great beasts shifting beneath the earth. In Japan, the Namazu catfish was believed to live underground and thrash when angered, causing tremors. In Native American folklore, earthquakes were the result of giant turtles shifting the land on their backs. These stories reflect an intuitive grasp of deep forces at work below our feet. While science has since replaced myth, the sense of wonder and humility remains. One of the lesser-known consequences of earthquakes is liquefaction, a process where solid ground temporarily behaves like a liquid. This happens when loose, water-saturated soil is shaken violently. The grains of soil lose contact with one another, and the water pressure between them increases, causing the ground to flow like mud. Buildings sink, roads warp, and entire neighborhoods can be displaced. This phenomenon was observed during the 1964 Nagata earthquake in Japan, and again during the 1989 Loma Prieta quake in California. It's a vivid reminder that solid ground is not always as solid as it seems. In addition to ground shaking, earthquakes can trigger landslides, avalanches, and tsunamis. A tsunami is not just a big wave. It's a series of waves generated by undersea earthquakes, landslides, or volcanic eruptions. The 2004 Indian Ocean tsunami was triggered by a massive undersea earthquake off the coast of Sumatra. Waves traveled as fast as 800 kilometers per hour and reached heights of over 30 meters when they struck land. The devastation was unimaginable, affecting millions of people and reshaping coastlines. Seismologists now work closely with oceanographers to develop better tsunami warning systems, though response time is still limited. Earthquake science continues to grow more precise thanks to global networks of seismic stations. Data from thousands of sensors worldwide feed into models that help scientists analyze the structure of the Earth's interior. These seismic waves travel differently depending on the materials they move through, allowing us to map subterranean features like magma chambers, fault lines, and even the boundary between Earth's mantle and core. Seismology, in a way, is the ultimate form of planetary sonar. Yet, even with this wealth of data, much remains unknown. Why do some faults slip quietly, producing slow quakes that cause no damage, while others store energy for centuries before unleashing it all at once? What causes one earthquake to be a solitary event and another to set off a cascade of tremors across an entire region? These questions drive ongoing research and fuel debates among geologists and physicists alike. Meanwhile, the Earth continues its restless turning, unbothered by our inquiries. Beneath our feet, forces are building even now, silently preparing for the next moment of release. It could come in a week or in 100 years. It might rattle a remote mountain range or a crowded capital city. Wherever it strikes, the story will be the same, an ancient process unfolding on a human stage, reminding us that we live not on a static planet, but on one in perpetual motion. To understand the full drama of earthquakes, we need to shift perspective. From the trembling ground under our feet to the layered architecture of the planet itself. Earthquakes are not surface events. They are born deep within the Earth's crust, where tension builds invisibly, far from human eyes. The crust, though rigid and fractured, is only a thin shell compared to the vast layers beneath it. Below the crust lies the mantle, and below that, the core. But it's within the brittle crust and the uppermost part of the mantle, together called the lithosphere, where most earthquake action unfolds. The lithosphere is divided into tectonic plates, each tens of kilometers thick and hundreds to thousands of kilometers wide. These massive slabs float atop the more ductile asthenosphere. But floating is not the right word, really. It suggests gentleness, calm. The plates grind, collide, and slide in ways that can reshape continents. Think of them as bumper cars, but in slow motion and with immense consequences. Where plates meet, the story changes depending on the direction and type of movement involved. At convergent boundaries, where two plates collide, the crust doesn't simply fold politely. One plate is usually shoved beneath the other in a process known as subduction. The descending plate is dragged into the mantle, heating and deforming. As it goes, these zones are terrifyingly effective at generating powerful earthquakes. Japan sits atop one such boundary, where the Pacific plate dives beneath the Eurasian plate. It's no coincidence that some of the most catastrophic quakes in recorded history have occurred there. But not all convergent boundaries are oceanic. When two continental plates collide, neither can easily subduct because both are buoyant. Instead, they crumple and push upward, forming colossal mountain ranges like the Himalayas. The collision of the Indian and Eurasian plates continues to this day, and with it, so does seismic activity. The region remains one of the most earthquake-prone on Earth. The very mountains that tower into the sky are a geological receipt of millions of years of seismic struggle. Transform boundaries, like the infamous San Andreas Fault in California, are no less dramatic. Here, plates move horizontally past one another. There is no creation or destruction of crust, only a prolonged, sideways shove. The friction between the plates prevents them from sliding smoothly. Instead, they stick for years or even centuries. When they finally do slip, the pent-up energy is released in a burst of motion that sends tremors racing through the earth. The San Francisco earthquake of 1906, which killed over 3,000 people and destroyed much of the city, was one such rupture along this boundary. Then there are divergent boundaries usually found along mid-ocean ridges. Here, plates are pulled apart and new crust is created as magma rises to fill the gap. While not as dangerous as subduction zones, these boundaries still generate earthquakes. They tend to be shallow and frequent, more a persistent grumble than a catastrophic shout. But given the vast extent of oceanic ridges, they account for a significant portion of global seismic activity. Even away from plate boundaries, earthquakes can still occur. These are called intraplate earthquakes. Their origins are less well understood, but they often result from ancient fault systems reactivating under new stress. The central United States, far from the edge of any tectonic plate, experiences such quakes. The New Madrid seismic zone, for example, has produced some of the most powerful earthquakes in North American history. In 1811 and 1812, a series of quakes shook the Mississippi River so violently that it briefly flowed backward. Though population density was lower then, similar quakes today could have devastating effects on modern infrastructure. The impact of an earthquake depends on more than just its magnitude. The depth at which it occurs, the type of soil in the region, the design of buildings, and even the time of day all influence outcomes. Shallow quakes tend to cause more surface damage. Soft soil amplifies seismic waves, increasing shaking. Unreinforced buildings crumble easily, while modern engineered structures might sway but survive. Nighttime quakes can be particularly deadly, catching people indoors and off guard. Daytime quakes might find people in open spaces or more prepared environments, slightly improving odds. Seismic risk is a complex equation. Scientists use hazard maps to assess which areas are more likely to experience earthquakes. These maps consider historical data, fault lines, soil conditions, and building practices. In regions like Japan and California, building codes reflect this risk. Skyscrapers are designed with shock absorption in mind. Bridges are retrofitted to resist collapse. Emergency kits, drills, and public education campaigns are common. Yet, in many parts of the world, such precautions are rare or poorly enforced. When earthquakes strike these areas, the results can be catastrophic. In 2003, a magnitude 6.6 earthquake hit the city of Bam in Iran. Over 26,000 people died. Many of the buildings, made of mud bricks, simply disintegrated. Contrast that with the 2011 magnitude 9.0 earthquake in Japan. Though more powerful, Japan's preparedness and building standards saved thousands of lives. The difference is stark and underscores a critical truth. While we cannot stop earthquakes, we can dramatically reduce their human toll. One of the most chilling aspects of earthquakes is their suddenness. They do not announce themselves with fanfare. One moment, the world is ordinary. The next, it convulses. There is no countdown, no warning siren loud enough to outpace the speed of seismic waves. The first sensation is often a low rumble, like a distant freight train. Then the floor sways, the walls groan, and the ground heaves. Objects fall, windows shatter, alarms scream. And in just seconds, the landscape can change completely. The largest earthquakes can rupture faults for hundreds of kilometers. The 2004 Indian Ocean earthquake, for example, ruptured a fault more than 1,300 kilometers long. The seismic waves it produced circled the globe several times, detectable by instruments everywhere. It triggered a tsunami that struck 14 countries and killed over 230,000 people. It wasn't just the quake, it was the chain of consequences. A single shift beneath the sea set in motion a wave that raced at jetliner speed toward unsuspecting coastlines. Seismologists study these events with increasing precision. Modern seismometers are sensitive enough to detect ground motions smaller than a millimeter. Networks of GPS satellites track the movement of tectonic plates in real time. Supercomputers simulate how seismic waves propagate through complex geological structures. Machine learning is being used to detect subtle patterns in seismic noise, signals that might otherwise be buried beneath the static. The goal is not only to understand, but to predict. But for now, prediction remains elusive. Instead, scientists focus on probabilistic forecasting. They can say with confidence that a fault is due for movement in the next 30 to 100 years, but not the exact day or hour. This frustrates the public and policymakers alike. People want answers, not probabilities. Yet, in the world of earthquakes, certainty is a luxury we do not yet have. The best defense remains preparation, not prediction. Civic planning, public education, and resilient infrastructure are the strongest tools we have. Some cities have even considered earthquake-resistant parks, open areas where people can gather safely during and after a quake. Technology plays a role too. Apps and early warning systems can give people a few precious seconds of notice. In those seconds, elevators can stop at the nearest floor. Gas lines can shut off, and people can duck under desks or move away from hazards. It's not a full solution, but it's better than nothing. In the meantime, the Earth waits. Stress accumulates along fault lines in a silence deeper than we can hear. The rocks bear their burden until they no longer can. Then, in a single shudder, they release their ancient tension. Buildings fall, rivers shift, roads twist. And we are reminded once again that we live on a restless, dynamic world. Beneath our feet, Earth is always in motion, even if that motion is imperceptible. It is easy to forget this as we go about our lives in buildings that seem solid, on streets that feel unmoving, and surrounded by landscapes that appear eternal. But none of it is still. The continents are adrift. The ocean floors are stretching. Mountains are rising and eroding. And deep within the crust, stress is accumulating along fractures old and new. Earthquakes are not rare events. They are essential expressions of how our planet breathes, shifts, and evolves. Every year, thousands of earthquakes shake the planet. Many are too small to notice, while others rattle windows, topple buildings, and fracture the ground. Each of these quakes has a story, a fingerprint of motion and pressure recorded deep below. Some earthquakes release only a tiny amount of energy, just enough to be picked up by a sensitive seismometer buried underground. Others release enough energy to rival the largest man-made explosions. The difference between them lies in how much. Stress the rocks have stored and how far the rupture spreads along a fault. Imagine a block of granite the size of a small town. It has been bent under pressure for hundreds of years. It groans silently, invisible to the surface. Then one day, it breaks. The fracture snaps outward, racing along the fault at several kilometers per second. This rupture radiates seismic waves in all directions, like ripples from a stone thrown into a pond. These waves pass through the Earth's crust and mantle, moving through rock with astonishing speed and power. Different types of seismic waves travel in different ways. Primary waves, or P waves, are the fastest. They move through rock by compressing and expanding it, like sound waves traveling through air. These are the first to arrive during an earthquake. And while they can be strong, they usually cause less damage. Secondary waves, or S waves, follow behind. They move the ground up and down or side to side, perpendicular to the direction of travel. S waves are more destructive than P waves and can cause buildings to sway dangerously. Then there are surface waves, which travel along the Earth's exterior. These waves are the slowest, but often the most damaging. They cause the ground to roll, ripple, and twist in chaotic patterns that buildings were never designed to handle. The complexity of wave behavior increases depending on the geological structure of the region. Seismic waves can bounce, refract, and slow down as they encounter different layers of rock, pockets of water, or underground caverns. In some places, waves are amplified, increasing the level of ground shaking. In others, the waves dissipate more quickly. This means two cities, the same distance from an earthquake's epicenter, might experience vastly different shaking based on the soil and rock beneath them. The influence of geology on shaking became tragically clear during the 1985 Mexico City earthquake. The epicenter was more than 300 kilometers away from the city, yet the shaking in Mexico City was catastrophic. Much of the city is built on an ancient lakebed composed of soft sediments. These sediments amplified the seismic waves, causing buildings to sway far more than those on solid rock. Hundreds of buildings collapsed and thousands of people were killed. It was a devastating lesson in how local geology can transform a distant tremor into a deadly disaster. Understanding these risks has become a priority for urban planners and engineers. In regions prone to earthquakes, building codes now include strict seismic requirements. Buildings must be able to withstand not just vertical loads from their own weight, but also lateral forces from shaking. In some designs, buildings are anchored to their foundations with flexible joints. In others, base isolators made from layers of rubber and steel allow the building to sway independently of the ground. Skyscrapers in earthquake zones often include tuned mass dampers, large weights suspended near the top of the building that sway in opposition to the motion of the building, reducing overall vibration. Despite these advances, older structures remain vulnerable. Retrofitting old buildings is expensive and time-consuming, but often necessary to reduce loss of life in future quakes. Bridges, schools, hospitals, and emergency facilities are particularly critical. If they collapse during a quake, the disaster becomes much worse. Governments around the world have invested in strengthening infrastructure, but the level of preparedness varies greatly from country to country. Wealthier nations tend to be better equipped, while developing regions often lack the resources to retrofit at scale. Aside from human construction, earthquakes also have profound effects on the landscape. In a matter of minutes, earthquakes can alter river paths, lift coastlines, drop valleys, and create new fault scarps. The 2016 Kokora earthquake in New Zealand lifted parts of the seabed more than 2 meters, permanently changing the coastline. The 2008 Sichuan earthquake in China triggered massive landslides that buried entire villages and blocked rivers, creating artificial dams and lakes that later posed additional flooding risks. Earthquakes also provide a rare opportunity to study the Earth's internal structure. Seismic waves behave differently depending on the material they travel through. by analyzing the arrival times and amplitudes of these waves at different seismic stations. Scientists can map the composition and temperature of Earth's interior. This method, known as seismic tomography, has revealed features like subducted plates deep in the mantle, magma chambers beneath volcanoes, and the layered nature of Earth's core. Seismic networks now span the globe, with thousands of stations measuring ground motion in real time. These data are transmitted instantly to research centers, where algorithms analyze them for signs of significant activity. In places like Japan, Mexico, and California, early warning systems have been implemented. These systems detect the fast-traveling P waves and send out alerts before the slower and more destructive waves arrive. While the warning time is often only a few seconds, that can be enough to save lives. Trains can stop, elevators can pause, gas lines can shut off, and people can take cover. The psychological effects of earthquakes are also significant. For survivors, the sudden loss of stability, both physical and emotional, can lead to long-lasting trauma. The sensation of the ground moving can be profoundly disorienting. After a major quake, people often report phantom tremors, a lingering sensation that the earth is still shaking, even when it's not. These experiences highlight how deeply our sense of safety is tied to the assumption that the ground is unmovable. Cultural responses to earthquakes vary widely. In Japan, children are taught earthquake drills from a young age, and businesses keep emergency kits on hand. In Nepal, ancient temples are built with flexible wooden joints that sway instead of SNAP. In California, buildings include evacuation maps and signage. These adaptations are part of daily life in regions where seismic activity is common. They represent a blend of science, tradition, and collective memory passed down through generations. Earthquakes can also trigger a cascade of other hazards. In mountainous regions, shaking can loosen rocks and soil, leading to landslides. These landslides can bury roads, isolate communities, and cause additional casualties. In coastal regions, undersea earthquakes can generate tsunamis, massive waves that travel at jetliner speeds across the ocean. These waves can arrive minutes to hours after the initial quake and often strike with little warning. The devastation they cause can exceed that of the quake itself. Entire coastlines can be erased in minutes. One of the most studied earthquakes in this regard is the Arlini Tohoku earthquake off the coast of Japan. The magnitude 9.0 quake generated a tsunami that killed over 15,000 people, displaced hundreds of thousands, and led to the Fukushima nuclear disaster. It was a sobering example of how multiple hazards can combine to create a complex and far-reaching catastrophe. Yet in every disaster, there is also a moment of insight. Each earthquake teaches something new about the Earth. Each rupture adds data to our models. Each aftershock becomes a point on a growing map of understanding. While we may never be able to predict earthquakes with precision, we are learning to live with them more wisely, to build more intelligently, and to prepare more thoroughly. Even in regions that have not experienced a quake in centuries, scientists keep watch. Faults once thought inactive can awaken with little warning. Historical records show that some areas now considered stable were once sites of major seismic events. The Earth forgets nothing. Its memory is stored in stone, folded in the layers of sediment, whispered along ancient fractures beneath the surface. The Earth is a storyteller, but its language is slow, and its messages are often delivered with sudden violence. Every earthquake is a chapter in the planet's geological autobiography, a pulse in the long narrative of shifting crust and changing landscapes. For all their terror and destruction, earthquakes also offer invaluable insight into the processes that shape our world. They allow us to glimpse the invisible forces operating beneath us, to understand that the ground we stand on is not fixed but dynamic, restless, and alive. Many of the world's most iconic natural landmarks are the product of seismic activity. Towering mountain ranges like the Andes and the Himalayas were born of tectonic collisions that lifted the Earth's crust skyward. Deep ocean trenches, like the Mariana Trench, are formed where one plate dives beneath another. Rift valleys, such as those in East Africa, mark the places where continents are slowly pulling apart. Earthquakes are not random acts of violence. They are milestones in these enormous geological transformations. In fact, the history of life itself is intertwined with tectonic activity. By shaping continents and rearranging ocean currents, earthquakes and the movements that cause them have influenced climate, migration, and evolution. The breakup of supercontinents like Pangaea set the stage for biodiversity to flourish on separated landmasses. The collision of India with Asia, which raised the Himalayas, also altered atmospheric patterns across Asia and helped drive the development of the monsoon system. But while plate tectonics works on a global and eon-spanning scale, earthquakes themselves are intensely local and immediate. Their effects are felt in homes, schools, hospitals, and workplaces. They are measured not only in magnitudes and epicenters, but in lives lost, homes destroyed, and communities disrupted. The ground might shake for only a few seconds, but the consequences can last generations. Recovery from a major earthquake involves more than just rebuilding structures. It requires addressing physical, emotional, and economic scars. Communities must recover trust in the stability of their world. Governments must assess damage, restore services, and provide aid. Engineers must analyze why certain buildings failed, while others stood, and scientists must gather data to better understand what happened and how to mitigate future risks. This post-earthquake period is also when patterns emerge that may be used to improve resilience. Certain types of buildings fail consistently, revealing flaws in design or construction. Certain soils liquefy more readily, indicating which areas need stricter zoning laws. And certain response efforts are more effective than others, pointing to best practices for future disaster planning. Each event, though tragic, becomes a lesson. In recent decades, a growing emphasis has been placed on community preparedness. Earthquake drills are now common in schools and workplaces in seismically active regions. Families are encouraged to prepare emergency kits with food, water, flashlights, and medical supplies. Apps and text message alerts can deliver real-time warnings. Even simple actions, like knowing how to turn off the gas line in your home, can make a difference. Despite these efforts, challenges remain. Many of the most vulnerable communities live in regions with poor infrastructure, limited resources, and little access to education about seismic risks. Informal settlements often grow rapidly on unstable ground, with no building codes or enforcement. In such places, earthquakes can be especially deadly. Addressing this global inequality in seismic safety is one of the great humanitarian and scientific challenges of our time. Meanwhile, technology continues to push the boundaries of what we can detect and predict. One promising area of research involves the monitoring of microseismic activity, tiny tremors that may signal changes along fault lines. These microquakes are far too small to be felt by humans, but can be detected by dense networks of instruments. In some cases, they reveal that a fault is creeping quietly. In others, they may indicate that stress is building toward a larger rupture. Another area of study focuses on slow-slip events, movements along a fault that occur over days or weeks rather than in a sudden jolt. These slow earthquakes release energy gradually, often without any shaking. They were first discovered in the 1990s and have since been observed in subduction zones around the world. Though not dangerous themselves, they may provide clues about the timing and behavior of more damaging quakes. Some scientists suspect they could act as precursors or even triggers. The use of satellite technology, especially GPS and radar interferometry, has revolutionized how scientists study deformation in the Earth's crust. By measuring changes in the ground's position over time, Satellites can detect where the surface is bulging, sinking, or shifting, even by just a few millimeters. These data help pinpoint zones where stress is accumulating. After an earthquake, satellites can also map how much the ground moved, often revealing complex and unexpected patterns of rupture. In the future, scientists hope to integrate all these tools, seismometers, satellites, machine learning, and field observations into comprehensive models that can offer better forecasting. The goal is not just to predict when a quake will happen, but how it will unfold, how the energy will move through the Earth, and how different regions will respond. It is a massive multidisciplinary effort, combining geology, physics, engineering, and data science. But perhaps the most powerful tool we have is memory, not just individual recollection, but the collective memory of communities. Earthquake. Memorials, museum exhibits, and anniversary ceremonies serve not only to honor the victims, but to remind future generations of the risks. They keep awareness alive in times of quiet, when the Earth seems still but is never truly at rest. This cultural memory is particularly strong in countries like Japan, where seismic history is long and deeply ingrained. Ancient texts describe quakes going back more than 1,000 years. Traditional architecture includes features designed to resist shaking. Even literature and art often include references to the impermanence of life, shaped by the reality of living on a volatile island chain. The result is a society that, while deeply respectful of nature's power, is also determined to coexist with it through preparation and resilience. In contrast, places with less frequent seismic activity may become complacent. A region that has not had a major quake in living memory may assume it is safe. But the Earth keeps its own schedule, not ours. Many faults go silent for centuries before releasing their stored energy in a single devastating event. Geological records found in sediments, tree rings, and cave formations reveal patterns that humans may have forgotten. These paleoseismic records show that quakes have struck before and will again. Understanding these records helps us plan for the future. Scientists study ancient tsunami deposits in coastal sediments, scour rock outcrops for signs of past ruptures, and use radiocarbon dating to build timelines of past earthquakes. This work helps fill the gaps in historical data, especially in regions without written records. It also expands our awareness of what is possible, of the magnitude, duration, and impact of past seismic events. Even our own bodies offer a kind of record. People who experience major earthquakes often carry the memory in their muscles and nerves for the rest of their lives. The sound of a rumble, the sway of a floor, the crash of glass, these sensations become imprinted. And while this trauma is real, it also contributes to a shared understanding, a communal readiness that can be passed on, taught, and honored. There is no doubt that earthquakes are among the most dramatic demonstrations of Earth's power. They strike without warning, they reshape the world, and they remind us that the planet is alive and evolving. They are not the result of human activity, nor are they punishments or omens. They are the outcome of deep, natural processes that have been operating for billions of years. Our challenge is not to stop them, but to live wisely in their shadow. The Earth is, in many ways, a machine built on tension. The tension between heat and cold, solid and liquid, expansion and contraction, pressure and release. Earthquakes are among its most immediate and visceral means of relieving that tension. But unlike other natural phenomena, like storms or floods, earthquakes offer no visual warning, no darkening skies or rising waters. They are nature's surprise events. And yet they occur with mechanical regularity when viewed across the vast scale of geologic time. Each tectonic plate interaction is like a loaded spring. Tension accumulates slowly, often invisibly, over decades or centuries. When the friction holding two sides of a fault together is finally overcome, the spring unwinds violently. The larger The area of the fault that slips, and the greater the accumulated stress, the more powerful the resulting earthquake. This is why some faults can produce magnitude 5 earthquakes every few years, while others remain silent for centuries before, producing a single magnitude 8 that shakes nations. In regions where these seismic springs have snapped before, geologists have mapped their faults, monitored their movement, and analyzed their patterns. Yet in many parts of the world, the full length and depth of fault systems remain unknown. Some lie buried under thick sediments. Others run beneath major cities. Many have not ruptured in the time humans have kept written records. These so-called blind faults are among the most dangerous because their silence can be mistaken for safety. When they finally move, they do so without historical precedent to guide expectations. One such event occurred in Northridge, California. In 1994, a magnitude 6.7 earthquake struck directly beneath the San Fernando Valley, on a fault that had not been previously identified. Buildings collapsed, highways buckled, and dozens were killed. The shaking lasted only 10 seconds, but the damage was immense. It was a grim reminder that the most dangerous fault might not be the one we know best, but the one we don't know at all. Similarly, in Christchurch, New Zealand in 2011, a magnitude 6.2 earthquake struck just months after a larger magnitude 7.1 event in a nearby region. The second quake caused far more destruction and fatalities due to its shallow depth and proximity to the city center. What made it especially troubling was that it originated from a previously unmapped fault. It tore through an area assumed to be moderately safe. The city was forced to rethink not only its recovery strategy, but its entire understanding of local seismic risk. Mapping hidden faults has since become a priority. Scientists use a combination of aerial imagery, satellite radar, ground-penetrating radar, and geological fieldwork to identify subtle signs of ancient ruptures. In some places, old fault lines are revealed by small offsets in river channels, scarps in the landscape, or patterns in soil deposition. In others, the signs are more elusive. Paleoseismology, the study of ancient earthquakes, has become a vital tool in this search. By excavating trenches across suspected faults and analyzing the layers of sediment, scientists can identify when and how past earthquakes occurred, even if they left no written trace. This long-view approach is essential because the recurrence interval of large earthquakes can be hundreds or thousands of years. A fault that ruptures every 900 years may seem inactive on a human timescale, but from the planet's perspective, it is simply biding its time. Paleoseismic studies in the Cascadia subduction zone off the coast of the Pacific Northwest have revealed evidence of massive earthquakes every few centuries, with the last one occurring in the year 1700. That quake was so powerful it generated a tsunami that struck Japan across the Pacific Ocean. The next rupture is a matter of when, not if. The Cascadia subduction zone is a chilling example of a silent but deadly seismic threat. Unlike the San Andreas Fault, which produces frequent smaller earthquakes, Cascadia has remained eerily quiet for over 3 centuries. When it does rupture again, the consequences could be devastating. Scientists estimate it could produce a magnitude 9 earthquake accompanied by a massive tsunami, inundating coastal towns and cities along the Pacific coast from Northern California to British Columbia. In anticipation of such events, governments and communities are slowly building resilience. Evacuation routes are being marked, early warning systems developed, and tsunami hazard zones mapped. Some schools and hospitals are being relocated to higher ground. Yet progress is slow and funding is often scarce. Preparing for a disaster that hasn't occurred in living memory is difficult in a world focused on short-term challenges. The development of earthquake early warning systems has been one of the most promising advances in recent decades. These systems don't predict earthquakes, but they can detect them as they begin. Because seismic waves travel slower than modern communication networks, It is possible to warn people seconds before the shaking reaches them. The effectiveness of this technology depends on a dense network of seismic stations, rapid data processing, and efficient communication channels. In Japan, these systems have already saved lives by giving people time to brace, duck, and take cover. Mexico also operates an earthquake alert system known as SASMEX, which has provided early warnings for cities like Mexico City when large offshore quakes occur. In California, Shack Alert is being developed to perform a similar function. These systems are complex and require constant updates, but their potential to reduce injuries and casualties is significant, especially in urban areas where every second counts. Another promising area of study involves the relationship between earthquakes and fluids in the Earth's crust. In some cases, the movement of water or gas underground can lubricate faults or increase pore pressure, making it easier for them to slip. This has implications not only for natural earthquakes, but also for those induced by human activity. Hydraulic fracturing or fracking has been associated with increased seismicity in certain regions. AS has the deep injection of wastewater and the extraction of geothermal energy. In Oklahoma, for example, a dramatic rise in small to moderate earthquakes has been linked to the injection of wastewater into deep underground wells. Prior to 2009, Oklahoma experienced only a few quakes per year. By 2015, it was experiencing more than 900 magnitude 3 or greater quakes annually. Regulatory changes and reduced injection volumes have since lowered the frequency. But the phenomenon has sparked new research into how industrial practices can destabilize faults. This intersection between human activity and seismic risk is also being examined in areas where large reservoirs have been constructed. The weight of water in these reservoirs can alter stress along nearby faults. The 1967 Koinanagar earthquake in India, which killed over 180 people, occurred near a newly filled dam and is considered one of the clearest examples of reservoir-induced seismicity. While such events are rare, they highlight how sensitive the Earth's crust can be to even small changes in pressure. Understanding these relationships is critical not only for safety but for policy. As societies continue to develop infrastructure and tap into new energy sources, the potential for triggering earthquakes must be taken into account. Engineers, geologists, and policymakers must work together to ensure that development does not inadvertently create new seismic risks. Despite all the complexity, the essential nature of an earthquake remains elegantly simple. It is the sudden release of stress along a fault. But wrapped within that simple definition are layers of science, engineering, history, and human resilience. Earthquakes have leveled empires, reshaped coastlines, inspired myths, and driven innovation. They are reminders of the raw power beneath our feet and of our need to understand, adapt, and prepare. Throughout history, civilizations have risen and fallen under the shadow of earthquakes. Some cities have been reduced to rubble in a matter of seconds, only to be rebuilt again and again atop the very faults that tore them apart. Others have vanished completely, lost to time beneath layers of sediment and stone. Earthquakes have no regard for human legacy. They strike where they will, indifferent to borders, wealth, or age. Yet despite this, humanity persists in fault zones, drawn to fertile valleys, coastlines, and mountains shaped by the very forces that threaten them. One of the most well-known historical earthquakes occurred in Lisbon, Portugal. On the morning of November 1, 1755, as citizens gathered for All Saints' Day Mass, a massive earthquake estimated to be magnitude 8.5 or higher struck the city. Buildings crumbled, fires broke out, and a tsunami swept through the harbor, killing thousands. The combined disaster claimed an estimated 60,000 lives. It shocked Europe and ignited fierce debates about science, theology, and the nature of divine punishment. For the first time, European society began to consider that natural disasters might not be the wrath of gods, but the result of physical laws. This philosophical shift laid the groundwork for seismology. It also pushed architecture and city planning toward more rational, safety-conscious approaches. After the Lisbon quake, new building codes were introduced, and tests were performed using miniature buildings and troops marching to simulate ground shaking. It was a crude but visionary start to what would eventually become earthquake engineering. Other regions have their own tales. In 1906, San Francisco was struck by a magnitude 7.9 earthquake. Fires ignited by broken gas lines burned for days. Over 80% of the city was destroyed. Yet even in the midst of catastrophe, scientists took the opportunity to study the effects. The earthquake led to the publication of one of the first comprehensive fault maps of California and solidified the idea of the elastic rebound theory. That quake, while devastating, became a turning point for seismology in the United States. Fast forward to 2010, and the story shifts to Haiti. A magnitude 7.0 earthquake struck near the capital, Port-au-Prince, killing over 200,000 people. The scale of the destruction was magnified by poor construction, lack of infrastructure, and decades of political instability. Hospitals collapsed, roads were impassable. Aid was slow to arrive. It was a heartbreaking example of how vulnerability can be amplified when preparedness is minimal. The quake highlighted the stark contrast between seismic hazard, which is a natural feature, and seismic risk, which is a product of human choices. This contrast is also evident when comparing to magnitude 7.0 earthquakes that struck within months of each other. One in Haiti caused extraordinary loss of life. Another in New Zealand in 2010 caused no fatalities. The difference was not in the geology, but in the preparedness. Christchurch had strict building codes and emergency services equipped to respond quickly. Haiti, despite the warnings of scientists, was unprepared. The lesson is clear. Earthquakes cannot be prevented, but disasters can. Beyond the shaking, earthquakes can awaken other hazards hiding within the landscape. In mountainous regions, the violent motion of the ground can dislodge rock and soil, triggering landslides that bury roads, rivers, and entire towns. In Nepal, following the devastating 2015 earthquake, more than 3,000 landslides were recorded across the country. Many remote villages were completely cut off, not just by collapsed buildings, but by walls of debris that blocked every route in or out. Helicopters became the only means of rescue or supply for weeks. In coastal regions, particularly those adjacent to subduction zones, the primary danger may not be the earthquake itself, but the tsunami that follows. These waves are generated when an undersea fault shifts the ocean floor, displacing vast amounts of water. Unlike wind-generated waves, tsunamis are long-wavelength phenomena. They may pass unnoticed in deep water, but as they approach shore and the ocean shallows, they rise dramatically. A tsunami can arrive within minutes, leaving almost no time to flee. Others may take hours, traveling across oceans and catching distant shores unaware. Japan's Arlene Tohoku earthquake illustrated the horror of such a chain reaction. The quake itself was massive, magnitude 9.0, and shook the entire country. But it was the tsunami, reaching heights of over 40 meters in some places, that caused most of the damage, swept entire towns into the sea, flooded a nuclear power plant, nearly 16,000 people. The images from that day of cars floating like leaves, houses crushed like matchsticks, and boats perched on buildings remain etched in global memory. The aftermath of such events is not only physical, but psychological. Survivors must contend with trauma, loss, and the long path to recovery. Children are often among the most affected, their sense of safety shattered. Schools, which should be places of shelter, sometimes become scenes of tragedy. In response, many earthquake-prone countries have turned their focus to making schools earthquake-safe. This includes strengthening structures, running evacuation drills, and providing psychological support after an event. The global community has also recognized the need for coordinated response. Organizations like the United Nations, the Red Cross, and various scientific agencies have developed international protocols for disaster relief. Satellite imaging helps assess damage in real time. Mobile hospitals are deployed. Teams trained in urban search and rescue fly in from around the world. Yet coordination remains a challenge, particularly when communication infrastructure is damaged or when local governance is weak. Technology continues to evolve. Drones now assist in mapping collapsed areas and locating survivors. Artificial intelligence is being used to analyze seismic data and detect patterns invisible to human eyes. Even the use of social media has become a tool for rapid damage assessment. Posts, tweets, and shared photos offer immediate clues about where help is needed most. In some countries, citizens can report shaking intensity through apps, contributing to crowdsourced earthquake intensity maps that fill in gaps between official stations. Yet despite all this progress, earthquakes continue to take lives. They strike without warning, and even the most advanced systems cannot always protect those most at risk. There are villages where no engineers have ever inspected the buildings. There are cities where warnings go unheard. There are moments when nature simply overwhelms everything humans have built. But this does not mean we are helpless. Education, preparedness, and investment in infrastructure remain our strongest defenses. Teaching people how to react during an earthquake, drop, cover, and hold on can save lives. Building with flexible materials, avoiding construction on unstable soils, and maintaining strict building codes are proven strategies. And maintaining awareness, even during long periods of seismic quiet, ensures that when the ground does move, the shock is met with readiness, not panic. Seismology as a science is a living discipline. It grows with every quake, refines its models with every aftershock, and stretches its reach with every new fault discovered. It is driven by data, but also by stories. Stories of survival, loss, and resilience. Each earthquake is a new entry in a vast library of tectonic history, and each survivor becomes part of the world's memory of that moment. In the end, earthquakes are not simply geological events, they are human events. They are tests of our understanding, our compassion, our planning, and our will to rebuild. The earth will continue to shift beneath us. That much is certain. What we do before, during, and after those shifts determines the kind of world we live in. The story of earthquakes is not just about rupture and destruction. It is also about the remarkable ways in which societies adapt, resist, and rebuild. In regions where the ground is known to tremble, architecture itself evolves in response. The ancient Inca, for example, designed walls that could withstand powerful quakes long before the science of seismology existed. In cities like Cusco, massive stone blocks were cut and fitted so precisely that no mortar was needed, and the walls could sway without toppling. These structures remain standing today, centuries after being tested by earthquakes that reduced modern buildings to rubble. In Japan, traditional wooden houses were built with interlocking frames that flexed rather than fractured. Their lightness made them less lethal if they collapsed, and their construction allowed for rapid rebuilding. In more recent times, Japanese engineers have become world leaders in modern earthquake-resistant design. From skyscrapers that sway gently like trees to suspension bridges that shift with seismic waves rather than fight them. The nation's infrastructure reflects centuries of living in harmony with an unstable landscape. Building for resilience requires deep understanding of local geology. A structure that performs well in one region might fail in another due to differences in soil composition, water saturation, or proximity to fault lines. In San Francisco, for example, skyscrapers are built atop deep piles driven into bedrock, bypassing the soft sediments that can liquefy during shaking. In Istanbul, concerns about aging masonry buildings have led to a push for seismic retrofitting. especially as the North Anatolian Fault creeps closer to another potential major rupture. Yet engineering alone is not enough. Culture plays a significant role in how people respond to earthquakes. In some places, earthquakes are met with stoicism, in others, with ritual. In Taiwan, shrines to earth deities are built beside homes to ask for protection. In parts of Indonesia, traditional houses are oriented to respect fault lines and believed to be spiritually fortified. These customs do not prevent seismic hazards, but they shape community, identity, and preparedness. They also serve as powerful reminders that humans have been interpreting, fearing, and adapting to earthquakes for millennia. One of the more subtle dangers of earthquakes is complacency. When a region goes many years without a significant event, collective memory fades, emergency kits are forgotten, building codes are relaxed, budgets are redirected. Then, without warning, the ground moves again, and the cycle of reaction begins anew. To break this cycle, some regions are developing permanent earthquake awareness programs. Schools conduct annual drills. Public transportation systems include seismic safety messages. Governments maintain public service campaigns, reminding citizens how to prepare, even when the earth is still. The importance of mental preparedness cannot be overstated. Panic is one of the most dangerous reactions during an earthquake. People freeze, run toward danger, or make irrational decisions. Training helps counter this. When individuals understand what's happening, they are more likely to act decisively and safely. Knowing to take shelter under a sturdy table, stay away from windows, and not to use elevators during a quake can save lives. Post-event education is just as important. Understanding aftershocks, knowing how to check gas lines, and recognizing signs of structural damage help prevent secondary disasters. As climate change accelerates, the relationship between natural hazards is becoming more complex. While climate itself does not cause earthquakes, it can amplify their consequences. Heavy rainfall, for instance, can saturate soils and increase the risk of landslides triggered by even moderate shaking. Melting glaciers in some mountain regions are altering pressure balances on the crust, possibly activating faults that have been dormant for centuries. The interaction of multiple environmental factors is adding layers of unpredictability to already complex systems. In urban areas, the threat of cascading disasters is particularly pronounced. A major earthquake might sever power lines, rupture gas mains, disrupt water supplies, and paralyze communication networks all at once. Fires can break out and spread unchecked. Hospitals may be overwhelmed or rendered inoperable. Rescue efforts become chaotic. This interconnectivity of urban systems, while efficient during normal times, becomes a vulnerability in crisis. That is why modern urban planning increasingly considers not only how buildings will survive a quake, but how entire cities will function in its aftermath. The challenge is immense. Cities like Tokyo, Los Angeles, and Santiago have invested heavily in seismic resilience. They've developed emergency protocols, installed early warning systems, and built with flexibility in mind. But other rapidly growing urban centers, such as Tehran, Jakarta, or Kathmandu, face huge obstacles. Densely populated, built with a patchwork of old and new structures, often lacking resources for large-scale retrofitting. These cities sit atop major faults and remain highly exposed. In rural regions, the challenges are different. Isolation can delay rescue and recovery. Infrastructure is often fragile. Traditional homes made from mud, brick, or stone without reinforcement are particularly vulnerable. After a quake, access to clean water, food, and medical care may be cut off for days. But rural areas also show unique resilience. Communities often rely on strong social networks, communal rebuilding, and knowledge passed down through generations. In places like the Andes or the Himalayas, villagers have rebuilt time and again, adapting their homes to the lessons of each quake. Globally, there is a growing call for earthquake resilience to be treated as a universal development priority. The United Nations has incorporated disaster risk reduction into its Sustainable Development Goals. International frameworks, like the Sendai Framework for Disaster Risk Reduction, encourage nations to assess their vulnerabilities, invest in risk reduction, and educate their populations. Funding agencies are increasingly tying development aid to resilience standards, especially in earthquake-prone regions. Science also continues to refine how we assess and describe earthquakes. While magnitude remains a key metric, other scales are used to understand the impact. The modified Mercalli intensity scale, for example, measures the shaking felt at specific locations. It ranges from barely perceptible vibrations to total destruction. This scale helps translate seismic energy into human experience. After a quake, intensity maps are used to estimate where damage is greatest and where help is needed most. In addition to ground motion, scientists are studying how buildings respond to shaking using real-time structural monitoring. Sensors embedded in skyscrapers, bridges, and tunnels record vibrations, stress levels, and tilt. These data help engineers understand how structures behave during actual earthquakes, allowing them to refine models and improve future designs. Some systems are even connected to automated safety responses, closing floodgates, pausing trains, or engaging emergency lighting. On a more experimental front, researchers are exploring whether earthquakes might emit electromagnetic signals or changes in underground gases before they strike. Studies in areas like China, Italy, and California have recorded unusual electrical, magnetic, and chemical anomalies days or hours before earthquakes. While none of these phenomena have proven reliable enough for prediction, they remain intriguing avenues of research. The dream of early prediction persists, and with each earthquake, new data brings us a little closer. Ultimately, living with earthquakes is about balance. We cannot remove the risk, but we can manage it. We cannot stop tectonic forces, but we can shape our response. Earthquakes are reminders of our planet's vitality. They are neither evil nor good, just natural. And in their aftermath, as dust settles and silence returns, we are faced with a choice. Do we forget, or do we remember? Do we rebuild the same way, or do we improve? Do we treat it as an anomaly, or do we recognize it as part of life on this shifting earth? The ground may shake again. It may surprise, terrify, and test us. But it also teaches, it humbles, and it connects us across cultures, centuries, and continents as inhabitants of a living, moving world. The deeper we explore the phenomenon of earthquakes, the more they reveal themselves as both destroyers and messengers. Their tremors are not just destructive forces, but signals sent from the depths of the earth. They carry with them stories of pressure and friction, of buried structures and subterranean boundaries. They remind us again and again that our planet is not a finished sculpture, but a work in progress. Beneath the surface, it stirs, shifts, and flexes, constantly rewriting the landscape above. In scientific terms, earthquakes are classified not only by magnitude or intensity, but also by the type of fault that generated them. Understanding the kind of fault involved helps seismologists model the behavior of future quakes. There are 3 main types: normal faults, reverse or thrust faults, and strike-slip faults. Each behaves differently, and each is associated with distinct tectonic settings. Normal faults occur when the crust is being pulled apart. They're common in regions where tectonic plates are diverging, such as the East African Rift or the Basin and Range Province in the western United States. In a normal fault, one block of rock slips downward relative to the other. These faults often produce moderate earthquakes, but can still be deadly if they occur near populated areas. Reverse faults, on the other hand, are the result of compression. They are found where plates collide, such as at subduction zones. One block is thrust upward over the other, often creating mountainous terrain. These are the faults responsible for some of the world's largest and most destructive earthquakes, like those in Chile, Japan, and Alaska. Their sudden vertical motion is also more likely to generate tsunamis if they occur under the ocean. Strike-slip faults involve lateral motion. The blocks of crust slide past each other horizontally. The most famous example is the San Andreas Fault in California. These faults tend to produce powerful quakes with significant surface rupture. They also lead to complex patterns of shaking because of their typically shallow depth and proximity to urban areas. In some regions, these types of faults exist side by side, interacting in ways that increase seismic complexity. In Turkey's East Anatolian Fault Zone, for instance, strike-slip motion combines with compressional forces from the collision of the Arabian and Eurasian plates. This interaction leads to a tangled network of stress that makes prediction and modeling particularly difficult. Beyond fault mechanics, scientists also study aftershocks, smaller quakes that follow a main shock. These occur as the crust adjusts to its new position. Aftershocks can continue for days, weeks, or even years, depending on the size of the original event. While smaller in magnitude, they are often more psychologically stressful for survivors and can cause additional damage to weakened structures. Aftershocks are not random. They tend to cluster near the edges of the rupture zone and gradually decrease in frequency and intensity over time. There are also foreshocks smaller earthquakes that sometimes precede a major event. Unfortunately, not all earthquakes have foreshocks, and not all foreshocks are followed by a main shock. This makes it nearly impossible to distinguish a harmless tremor from the beginning of something larger. Nevertheless, patterns of foreshock activity are being studied with renewed interest, particularly with the help of artificial intelligence and machine learning, which can sift through vast datasets for subtle signs missed by human eyes. One of the most compelling aspects of earthquake science is its intersection with human time. Geological processes typically unfold over spans that dwarf a human lifespan. Mountains rise over millions of years. Ocean basins form and close over hundreds of millions. But earthquakes condense that geologic time into moments. In a matter of seconds, they can expose weaknesses that took eons to develop. They act like photographic flashes, briefly illuminating the invisible forces shaping the crust. Seismologists use each earthquake as an opportunity to peer into the Earth's interior. They study not only the event itself, but the waves it generates, how they travel, reflect, refract, and attenuate. These waves provide clues about the structure of the crust, mantle, and even the core. Over time, data from thousands of earthquakes have allowed scientists to build detailed models of Earth's internal architecture, including the discovery of deep mantle plumes and large low-shear velocity provinces that may influence surface, volcanism, and plate movement. But for most people, the relevance of earthquakes lies in their immediate impact, how they affect daily life. Whether it's a child in a schoolroom, a surgeon in the middle of an operation, or a commuter on an underground train, the moment the shaking starts, instinct and preparation take over. That's why public education is such a critical component of earthquake readiness. Drills, simulations, and school programs aren't just bureaucratic routines. They're rehearsals for survival. Community-based preparedness programs have proven especially effective. In Japan, entire neighborhoods are organized around local disaster response teams. Residents are trained not only in first aid and rescue, but also in how to work together during and after a major quake. These community ties often make the difference between chaos and order in the crucial hours after a disaster. In Chile, similar programs ensure that families know evacuation routes and assembly points for tsunami-prone areas. The principle is simple. The more informed and connected a community is, the better it weathers a crisis. In the scientific community, the dream of predicting earthquakes with reliable accuracy remains distant. But forecasting, understanding the likelihood of a quake occurring in a specific place over a specific time frame, has improved significantly. Probabilistic seismic hazard assessments combine geological records, fault mapping, historical data, and computational models to estimate risks. These forecasts are used to update building codes, insurance rates, and emergency plans. Still, gaps remain. Many cities sit atop faults that have not been studied thoroughly. Others continue to grow without adequate zoning or safety regulations. And some regions, even those with known risks, lack the political will or economic resources to address vulnerabilities. In these cases, the question is not if a disaster will occur, but how bad it will be when it does. Part of the challenge is that seismic safety competes with other urgent priorities: poverty, education, healthcare, and economic development. For many governments, allocating millions for retrofitting schools and bridges is politically difficult. When immediate needs dominate the agenda, but the cost of inaction is usually far greater. Every dollar spent on preparedness saves many more in recovery. Every building made resilient is a life potentially saved. Perhaps one of the most important messages earthquakes teach us is humility. No matter how advanced our technologies become, or how vast our scientific understanding grows, the Earth remains a force beyond our control. We can measure its pulse, study its scars, and anticipate its behavior, but we cannot tame it. What we can do is adapt through learning, through planning, and through a shared commitment to resilience. In the end, earthquakes challenge more than just our infrastructure. They challenge our sense of permanence. They challenge our confidence in stability. They remind us that even the most familiar landscapes are temporary arrangements of matter, shaped by processes that began long before us and will continue long after. But within this instability, there is also beauty. The valleys, cliffs, islands, and ridges we admire are all the handiwork of tectonic artistry. The Earth shakes because it is alive. And so, we arrive at the final tremor in our exploration, a reflection not only on why earthquakes happen and how they work, but what they mean for us as a species living on a restless planet. Earthquakes are not just geological events. They are reminders that change is inevitable, that control is fleeting, and that adaptability is not a luxury, but a necessity. They invite us to think about where we live, how we build, how we prepare, and how we respond when the unthinkable suddenly becomes reality. Every fault line is a reminder that the Earth is divided, that its surface floats in sections across a molten, dynamic interior. But every earthquake also connects us, whether it's a tremor in Nepal felt halfway around the globe by seismographs, or the global outpouring of aid after a major disaster. Earthquakes respect no borders, and neither should the collaboration required to understand and live with them. Some of the most promising efforts in earthquake research now lie in international cooperation. Networks of seismic stations across continents, satellite systems that monitor ground movement from orbit, and data-sharing initiatives that cross political divides all represent a growing recognition that no nation can tackle seismic risk alone. The Earth is shared, and so is its restlessness. This global perspective is also changing how future generations are being educated. In regions once passive in the face of earthquakes, children are now taught not to fear the ground, but to understand it. Science classes include modules on local fault lines. Schools practice drills as regularly as they practice fire safety. In cities from Tokyo to Istanbul to Santiago, earthquake awareness is becoming part of cultural identity, woven into how people build, plan, and even think about time. Meanwhile, urban design is evolving in response. Architects are exploring not just how to prevent collapse, but how to design cities that can quickly recover. This includes resilient corridors where critical services are concentrated and fortified. redundant power systems, modular buildings that can be disassembled and reused, and even public spaces designed to double as emergency gathering zones. Some forward-thinking cities are incorporating seismic memory into their architecture, building monuments and museums on fault lines to preserve the history of past quakes and educate about future risks. Art, too, plays a role in how we process earthquakes. In the aftermath of major tremors, people turn to song, painting, poetry, and film to express grief, resilience, and hope. These cultural responses become part of a society's healing process, as important in some ways as the rebuilding of roads and homes. They serve as living archives of emotion and experience, and they keep the memory of each quake alive in a different kind of register, one that resonates in the heart, not just the ground. We should also acknowledge the silent guardians in this story: the scientists, engineers, first responders, and community organizers who dedicate their lives to preparing for earthquakes that may or may not come in their lifetimes. They operate on borrowed time, hoping that their work today saves lives tomorrow. Many of them work in relative obscurity, their names forgotten once the headlines fade, yet their impact may ripple through generations. As our understanding deepens, one question remains both scientific and philosophical. What is the acceptable level of risk? How much safety is enough when perfection is impossible? Should cities be abandoned if they sit on dangerous ground? Should we restrict where people can live, or focus instead on building smarter and responding faster? These are not questions with easy answers. They touch on issues of freedom, equity, tradition, and survival. In some parts of the world, entire towns have been relocated after devastating earthquakes. In others, people return year after year, rebuilding in the same spot. There is no universally right choice. What matters is that the choice be informed, that it arises from a clear-eyed understanding of the risks, not from ignorance or denial. That it balances memory with foresight. The Earth will continue to surprise us. There will be more earthquakes. Some will be small and harmless. Others will bring unimaginable destruction. But every single one will offer data, insight, and perspective. Each tremor is part of a larger narrative, a story told in fractures, and folds in uplift and subduction, in silence and in sudden jolts. We have journeyed from the deep interior of the planet to the peaks of seismically formed mountains. We've followed the shaking ground through cities, villages, ancient ruins, and futuristic urban cores. We've learned that the Earth's surface is not solid ground, but a living map of movement. And we've seen that human survival depends not on certainty, but on preparation. Thank you for watching this video on the Sleepless Scientist channel, where science meets relaxation and a sprinkle of insomnia. We truly appreciate your time, and we're sorry if learning about tectonic forces made your eyelids resist gravity. If your heart raced a bit thinking about fault lines under your feet, we hope at least your mind is resting easier with knowledge in place of worry. Before you drift off or stay up mapping your local seismic zones, we'd love for you to like this video, subscribe to our channel, and comment with where you're watching from and what time it is there. Are you in a quake-prone city? A peaceful prairie? Share your thoughts, stories, or just a sleepy hello. Now, to help you relax after all this geological excitement, we're transitioning to a gentle audio segment with soft ambient sounds to guide you into a restful sleep. Close your eyes. Let the stress slide off like tectonic plates under a warm ocean. And know that while the Earth may shift and tremble, tonight you are safe. Good night.